This moved, and it moves so fast that you can watch it move. One of the things that it does that's pretty remarkable is over here. This is a big carpet roll of organics that the Lobe, acting like a bulldozer, just pushes up and rolls it up. In 2011, I have a photo of it where it was out in the trees and it was fairly far ahead of the toe. Now it's eating it. The toe is eating where it's pushed the organics up, and there's a bunch of silt that's deposited over the top of it, so it's being consumed. We have some time-elapse photography of the toe changing, trees falling down, rocks falling down. It's very dynamic. It's very dynamic. We have a pretty wet year this year as far as the summer goes. A lot of the water in these lobes probably come from the catchment area, rainfall events during the summer, snowfall and snow melt in the early spring, and that all collects and comes into the lobe. FDLA moves two ways. Most of it is in the shear zone, 66 to 74 feet below the surface, and then there's another minor portion which is internal flow, so the whole thing is flowing as well.
So the shear zone is underneath the frozen debris. What we call the core lobe is moving in a path, and it's sliding on the frozen ground underneath it. There's a zone in there below freezing in temperature, but it is not frozen. The liquid water is still there. And so that makes it a unique situation. So you have liquid water at a negative temperature, which is what we call supercooled water.
Movement occurs all winter long, and it may be due to this water that is under high pressure and yet at sub-freezing temperatures, which is a conundrum to wrap your head around.
But the temperature lowers that pressure, and so the colder the feature is, the less pressure there is. Because if the pressure goes up, the whole lobe is lifted and starts floating. And so my solution would be to cool the lobe, but it's very expensive to cool the lobe.
Big, huge!
Big hole.
With ice!
It's frozen material, it gets warmer because there's this pit, and because it gets exposed to the air and the sun. And the more ice that is in your wall, the easier it is for that to continue thawing. And so we go retrogressive because typically it goes uphill, as you saw also today. And the material just runs downhill.
Right here.
Oh yeah.
What we found there today was very interesting, is that we found this ice there, this massive ice.
We had hypothesized that the cracks on the surface might be one avenue for water infiltrating down into the lobe.
That's all ice there, huh? This is solid. Wow.
A faster avenue for water migration than through the soil down to the shear zone. Today we found massive ice that there was a break in the organic material, and there was a crack on the surface that corresponded with some massive ice.
What was really astonishing that it had changed so much since last year. It's really a question what the future will bring there, because as I said, the more ice there's in that wall, the faster it will go, and it doesn't stop. Meaning it's now at a size where it could take a whole section of the lobe away.
Each one of these little arrows represents a place where we have a surface marker. And the numbers are distance it moved from June of 2013 to June of 2014. So over a year, the numbers are in feet. At our uppermost points, it's moving about 20 feet a year right now. And in the middle, 15, down at the toe, about 13 feet. So it's moving faster at the top than at the bottom. We would think that means it's thickening up in the middle. We're just looking at the data this week, and we might be able to see that also. So it's pretty substantial movement.
Slope movement is so rapid up here. I mean, compared to other areas, a lot of places have slope movement and it's pretty slow and downslope. And this is a very fast movement. I mean, it's not instantaneous, but it's certainly fast enough that on a year-to-year basis or even every couple of months, you can see the dynamic changes. And I think that that's what impresses me the most about these features.